start the recording now. All right, and let me share my screen with you as well. Okay. Can you see my share screen now?
Something just happened to mine. Hang on.
Okay. Yeah, I can see yours.
Okay. Very good. All right. Okay. The material today I am going over for you is more abstract and maybe a little bit challenging.
Hey, Professor.
Oh, yeah.
I have a really quick question before we dive into this week's lesson or next week's lesson. On the midterm, the R project, just to make sure, because I submitted it, but I guess I have a little bit of a question. When it comes to the 4 different iterations of the sample sizes, did you, along with the image, the histogram, did you want us to also explain after the pictures, explain the pictures, like explain the images, basically, obviously from 5 to 60, the central limit theorem really kicks in and you can really see the difference, right? Did you want us to talk through that on the midterm project or simply just give you the images?
Definitely. It's expected that you give explanation because that shows your understanding of the theorem.
Okay.
Yeah, that's a point. That's a key point. If you did not put your explanation in there, you can submit a second one. I mean,
okay.
With the explanation. Because
I talked about the central limit theorem on the 2nd page, but then on the 3rd and 4th page, I basically just gave you the R code and the histogram. I didn't explain obviously the visual, and I was wondering if it just kind of seemed like maybe I should do that. So okay.
But yeah, that will be essential because that explains why central limit theorem works, why it's powerful, because as in the repeated sampling, when the sample size increase, the sample standard deviation, or we call it sampling error, becomes smaller by the scale of 1 over square root n. And so as n increase, and you can see the variability decrease, and right. to such an extent that as n approaches infinity, which is as a small sample size approach a population size, it was become a point, right? And because the sigma divided by square root of infinity becomes 0, and that means all the points coincide at 1, and that means if you take a sample, the size of the population, then there's no error. Your sample mean is your population mean.
Right. Okay.
Yeah, that is central limit theorem. Everything is centralized through the larger sample, at least 30. Everything can be approximated. I mean, everything means the sampling distribution of the sample mean will be able to be approximated by normal distribution. And that is a powerful theorem because regardless of the population from which the sample is taken, it may be discrete, may be uniform, may be exponential, all have different shapes, unimodal, multimodal, those doesn't matter. As soon as you start to sample, even with the size of 2, the sampling distribution of the sample mean start to bend, taking the shape of the normal, and that become especially obvious as an increase to 30. Yeah, so that's a power of theorem. Yeah, so that as many of you discussed, it's essential for that for central limit theorem. Otherwise, if there's no central limit theorem, the inferential statistic may collapse. In a sense, yeah. Okay. Yes. So hope that answered your question.
It does. Yes. Thank you.
Okay. Okay. No problem. Okay. So for today, I would just go over the textbook in this way because it's okay. You when you study it, you can study in a sequential way in this order. Okay. Now we are going to cover 5.2, 3, and 4 about and they are all about the point estimators and unbiasedness, and then the pivotal method. Why are we covering this chapter? Because we want to estimate the population parameter. The population parameters, there are a few of them, quite a few of them actually. As I may have mentioned before, in statistics we describe data in 5 aspects mainly. The first is the population, is the mean, is the center. Of course, not just mean, but mean, median, mode. Then variability. We want to describe how widely spread out is the data, and that is a variability. And the measure for describing it is mainly variance or standard deviation. Then we talked about probability, shape, and outlier. And these 5 aspects are the area that we describe. But in terms of when it's come to population, we don't have the way to describe the mean because we don't know the mean. Why? Because unless you take a census, which is usually very expensive and time consuming or resources consuming, so literally impossible to have census, right? Regardless what area of study of interest to you, it is because the population is constantly changing and the status is constantly changing. For example, even the income, what's the average income for the young adults in their 30s in the United States? What's the average income for population in that age bracket? It's hard to, nobody really know in a real-time way. So that per se, we don't know the mean, mu. And so we need to find an estimator, and that's the point we are going to look at here, point estimator. A point estimator for mu is x bar, simple mean. So it's make every sense to say that to estimate the population mean, we use a sample mean. And later we can prove that the average of the population mean will be equal to the, the average of sample mean will be equal to the population mean. And then that's a first estimate, point estimate, point. And the second one is the estimator for variance, population variance. And we use sample variance to estimate population variance. But what kind of sample variance do we use so that it's an unbiased estimate of population variance? When I say unbiased, that means the average of it will be equal to the population parameter. So in this case, you can see that at the bottom of this formula, many people may wonder why don't we use the same formula like n 1 over n, but we have to use n minus 1? Because the reason is because the exactly the same reason that I said just now, because we need an unbiased estimator. Because if according to our intuition we use an n, and that will cause us to underestimate the population with such a simple mean as an estimator, that will systematically underestimate the population standard deviation or variance. Yeah. So that's why we need to recalibrate it by subtracting n by 1 to give a little bit higher estimate of the sample variance and therefore population variance. Okay, right. So these are the point estimators. X bar is a point estimator for mu. S square is a point estimator for sigma square. Okay, so this is the reason why we look at it. Okay, and you can see that B is a bias, and expected value of sigma hat, according to the notation here, is sigma hat is the estimator, sigma is a parameter, and E sigma hat is expected value, that is the mean. When you take the repeated sampling of same size, okay, then you take the average of all the means, take the mean of all the means, that is what is mean here. It will be, and find a difference between the population parameter, in this case population mean. Well, whether there is bias or not will determine if it is unbiased estimator. If we use X bar, then the B should be 0. That's why it's unbiased, and so forth. Okay. Then we first, of course, before we see the proof, we want to see the methods of moments. Okay, here you have mu k prime equal to E x to the power k, and we see mk prime 1 over n summation, that thing in the sigma. So one is called kth moment about the origin of a random variable x, and for the population, and m is the corresponding kth sample moment. So we use plan to denote the moment, and but which moment we use k? We use k to denote the kth moment. There's first moment, second moment, third moment, and fourth, so on and so forth. And then the mu stand for population, and m stand for sample. So mu k plan is the population kth moment, and that's equal to the expected value of x to the kth power. And yeah, so on and so forth. All right, so with that, let's show an example. For example, here, and the first moment, population moment is mean. Yeah, that's a mean. Mean is the first moment. And the first sample moment, and of course, is sample mean. So population mean, mu is the first moment of population, and sample mean is the first moment of sample. Yeah. Then the so the moment estimated of mu1 is x bar. We don't know mu, the first moment of population, but we can use the first moment of sample to estimate it. If k is 2, the second moment, then y2 prime is like that, equal to e expected value of x squared. And the sample moment, the second sample moment is like that. I have highlighted. And we use the second sample moment to estimate the second population moment. Yeah. Okay, so that is the rationale. And let me use an example to see. Yeah, then we use a 552 example to illustrate. Okay, suppose for a gamma distribution, you will just refer to this section, and we'll see that the gamma distribution has two parameters, alpha and beta. And we know for any population distribution, there's at least 1 to a few, 3 or 4 population parameters. What the function of the parameters is to determine the center, and which is the mean, and the standard deviation of the population. Of course, probability as well, shape as well, and because when the parameters is determined, everything is determined. Okay, the population parameters determines everything about the population, about that distribution. So now when you refer to 3.25, you see the sample, the mean is equal to alpha times beta, and then the expected value of x squared is that. Okay, so with that, we can, with these, obviously, they are the first and second moment, because according to the formula, the first moment is expected value x to the power 1, k equal to 1. And the second moment is expected value of x to the power of k equal to 2, right, for population first and the second moments. Now, what about the first and second moment of the sample? The first moment of sample is sample mean. The second moment is the average of the sum of the squares of each variables. I mean, in the of the n observations. So yeah, you go back and look at this formula, you will see. So we can just equate the sample moment, first sample moment, to first population moment, because they are estimators. So sample mean is estimated to the as a sample mean as a first sample moment is, and the bias is an estimator to that of a population, first population moment. And the second sample moment is an estimator to that of a population, second population moment, right here. So Okay, so now you have two equations. Alpha, beta are unknown. The others, like x bar and this sum of x bars I squares are known. So can you solve this equation, simultaneous equation, to solve for alpha and beta? Then the solution will put a hat. We call it alpha hat and beta hat. Okay, so yeah, I think you should have no problem doing this. Okay, so you will get the alpha hat and beta hat as shown here. All right. So the rationale is just to you equate. We define the equation first for population moment, kth moment, population first moment, population second moment, and so forth. And we also define the sample moment, sample first moment, sample second moment, and so forth. Then the way to get them estimate for the parameters through the method of moment is to equate the population first moment to sample first moment, and then equate the population second moment to sample second sample moment, and then solve for that equation. You will be able to obtain the estimator for those two population parameters, alpha and beta, but we denote them by alpha hat and beta hat. And so this kind of estimator, we call it estimators from the method of moment. Okay, yeah, the method of moment. We call it moment estimators. Okay, moment estimators. Okay. The third example, excuse me. Third example, we have the values here, and so what that means is you repeat a math. I mean, use the same rationale. Equate the first sample moment to that of population moment. Population moment is mu, and sample moment is sample mean. Okay, x bar. Then the population second moment. Population second moment is like here, but its share is here. Okay, so variance is equal to the expected value x squared minus mu squared, but the expected value x squared is the second population moment. So you rewrite, then the second population moment is sigma squared plus mu squared, because variance x is sigma squared. Then you equate this to what? The second sample moment, which is this. So you get equation again, and then you will solve for mu, solve for sigma square, but you put a hat on both of them to denote that they are moment estimators. Okay. And then you actually plug in the numbers, and then you can calculate the value of these two moment estimators, right? So this is, I think you look at the 3 yourself, and 5, you will be able to figure that out and get a hang of it. Okay, how to get the moment estimators. Okay, thereby equating the same population kth moment with sample kth moment respectively, and solve the equation, then system of equation to then you will get the moment estimators. Okay. Now, so that being said, we don't just have a way to estimate the parameters. Another useful way to estimate it is proposed by Fisher, Ronald A. Fisher, in 1922. So it's called the method of maximum likelihood. Well, by its own name, we know that it has to do with likelihood. But what kind of likelihood? The maximum likelihood. So, so here, if you look at the probability, so the likelihood of the set of parameters theta given x1 to xn is equal to the probability of those observed outcomes given the parameter values. So if x1 to xn are discrete IID and with probability functions p, x, and given theta, then the likelihood function is the product of this. Okay. And so if it is continuous, this is for discrete, and so this is for continuous. And so that means you plug, what that means is you simply plug the parameters in and the data into the PDF function respectively for n times. Okay. In other words, you have a sample. The sample has small n observations, and then you have a set of parameters. Then you plug this parameter and the data into the PDF function. Okay, but then you will have n such functions, n such PDF functions. Okay, with only each one has different observations plugged in. And to find a product of them, we call it, you get a likelihood function. Then you take the log function of the likelihood function, and then take derivative with respective to the parameters and set them to 0. If there's only one, then set it to 0 to solve that equation to get this theta as a estimator, as a maximum likelihood estimator. And if there's more than one parameter, then you take the partial differentiation with respect to the functions, the parameters, and then solve for the system of equation. Okay. Let me see. For unlimited. Okay. Let me see. Our whenever we got cut off, as you can see, I am not using a pro version, so we may be cut off after 40 minutes, and we will resume. Okay. We'll just come back in. We'll continue until we get done. Probably today we don't have time to cover the assignment, but I think these examples will suffice for you to work on them yourself. Okay, so here we have example 526. Now, how this give you idea how to get the likelihood function. So first of all, show the PDF, which is like that, and you have sigma and mu in there. So what you should do is you plug in x1, you get the function likelihood function based on x1. Then you plug in x2 in the in a PDF function, you get another PDF function based on x2, so on, and until n xn, and then you multiply them, you get a likelihood function. But we need to calculate maximum likelihood, not just any likelihood. So I'll skip that. And then, so for the procedures to find it is what I described. First, find the likelihood function like you just saw in the normal distribution likelihood function. Then take the natural log of that likelihood function, and then differentiate it with respect to theta. Equate the derivative to 0. Then solve for the parameter theta, and you will obtain theta hat. Okay, and whether it is a maximizer or a global maximizer. Okay. So here is an example. For Bernoulli, you have p times 1 minus p x minus 1. Oh, sorry, geometric. Okay, and so you plug in the x1, x2 to this PMF function, and then take the product. Okay, but then take the natural log. You see, you got this. Then you take the differentiation. There's only one parameter, p, so just do the differentiation with respect to p of the log likelihood function and set it to 0. You will be able to solve for p. Then you can obtain it and say that this 1 over x bar is the maximum likelihood estimate for p, because this p, it plug in the function based on the sample of x1, x2 to x more n. You will be able to maximize the likelihood. Therefore, it makes the likelihood it gives you the maximum likelihood. So it's a good estimator for the p. That's the rationale. Excuse me. Okay, then 528, the same rationale. Still, we only have a parameter lambda, and so we do the same thing, similar to a previous one. We take the natural log differentiation with respect to lambda, set it to 0. It will be x bar. All right, so these are more straightforward, and I will. But for this one, 5 to 9, you will see that there is this is the uniform distribution. But uniform distribution, you don't have it doesn't have to do with data in a sense, because they are not even in a function. So we have to look for the graph and determine. So here we have 1 over theta to the power of n. Okay. All right. So this one, if you look at the graph, you can only take the maximum of xi, which will make let me see the end. What will maximize the maximum of xi? Okay, here it says when theta greater than the maximum xi, the likelihood is that, and so greater than maximum I greater than, which is positive and decreasing function of theta. If this is a minimum value of theta can be chosen, as we will not be able to find its derivative. So this statement says we cannot find its derivative, but 5.1 shows that the maximum occur at the point where maximum likelihood occur at this point of x n, which is the maximum of xi, and so the the maximum likelihood estimator is the order statistic. Okay, yeah. So at the maximum likelihood value, the maximum of this the x in the range, this xn maximum will give make likelihood largest, and so that's why it's a estimator. Okay. And then let's see, for the sake of time, let's skip this one. So then you can follow this line of thought. Now here we have two parameters. So as I mentioned, for the two parameter case, their distribution were two parameters. So for two population parameters case, you do the partial differentiation and then solve for the system of equation to derive the solution. Okay. Okay. Excuse me. All right, let's move on to 5.3. For the sake of time, it's already 40 minutes. By the way, in about 1 minute, we may be cut off, so just come back in immediately when we are cut off in 1 minute. Okay. 5.3.2, we'll skip the sufficiency. So we finished 3.53 already. 1 second. We finished the sufficiency. We don't cover sufficiency. Okay. We maximum likelihood estimator. Yeah. Okay. Please come back now. It's getting cut off in 10 seconds. All right. So we will come back. Okay. 5.3. We'll come back and look at 5.3 and 4. Okay.